Section 2, we start dealing with, instead of just points in 3 space, we're going to look at vectors in 3 space. Okay. The nice thing about it, just like the first section, it's pretty much just tack on the z, tack on the third value for each. So if you look at your primary unit vectors that define the axes, well, you still have I is still going along the x-axis. The vector I is 1, 0, 0 instead of just 1, 0. The vector j is 0, 1, but then you got to add on the 0 for the z. And k going up the z-axis is 0, 0, 1. Okay. Notation-wise, you can get your standard form, or your standard unit vector, is just v1 times whatever I, j, and k are for each of those things. Okay, that'll extend or shrink it however far you want it to be. So standard form is going to have that number times I plus number times j plus number times k. Honestly, I'm not going to use that form most of the time. What was the other form called? Anybody remember? Stretching back to last semester. No, that's this one. Component form. It's the one where you have the arrowed brackets. Remember that one? Yeah, this is going to be one of those lessons where it's like, oh yeah, I do remember vaguely doing that. So the idea of component form is repositioning the vector wherever it currently is so that its initial point is on the origin. Well, the way you do that's the same way we did it before. You take the terminal point minus the initial point. Okay, so wherever your stopping point is, just subtract the x, y, and z values from their corresponding parts. Okay? All your same rules pretty much apply as well. Now this box is in the book if you want it, but you have two vectors can only be equal if all their corresponding components are equal. Well, that makes sense. If you put it in component form, x, y, and z should all be the same thing. Magnitude, that's just the distance formula. But the nice thing is, because this thing has the initial values at 0, right? You don't have to bother with any of them. You just square each individual value. Since it starts at 0 and goes to this u1, u2, u3, just square them all, add them up, square root. Unit vector is the exact same. All you do is take whatever your current vector is and divide by its magnitude. So take all 3 values in the current vector, find the magnitude, and then divide by that. It's shrinking that vector so it's only 1 unit long. Adding them up, just adding their corresponding components. Scalar multipliers, just distributing whatever's out front to all the components. And dot product is when you dot 2 vectors together, you multiply their corresponding parts and add everything up. Vague recollection from last semester? Okay. And that's all in the book too, if you want to copy them down for notes. But let's actually make use of them. Find the component form and the length of vector v with initial point at 2, 4, 1, terminal point 3, 5, 2. So how do I do it? Yeah, just subtract them. So I'm going to make the vector v, well, in here, which one am I going to subtract from which? Yeah, the 2, 4, 1 from the 3, 5, 2. So 3 minus the 2, 5 minus 4, 2 minus 1. Giving you what? 1, 1, 1. What would the length of that line be? Square root of 3. Because the magnitude is going to be equal to the square root of 1 squared plus 1 squared plus 1 squared. In other words, square root of 3. So those are your first 2 answers. Then it asks you to find the unit vector that's going in that same direction. Yeah, take each one of these over the square root of 3. The unit version of this, you just take vector v divided by its magnitude. So it acts as a scalar multiplier, essentially. You're multiplying by 1 over that square root of 3. So in other words, that's going to give me what? Square root of 3 over 3 for all of them. Make sense? Okay. Dot product. What would be the dot product of these two vectors? Two. Negative 1 times 0 is 0. 3 times 4 is 12. 5 times negative 2 is negative 10. So you get 2. Notation's just different, but all the arithmetic part of it's easy. Now, if you want to find the angle between two vectors. Now, the nice thing about two vectors in space, it actually ends up being the exact same formula. And the reason why is, no matter where you have two vectors, well, if you take those vectors, move them to the origin, okay, because remember, they can be anywhere, right? If you take them and move them so that they're in component form, so they start at the origin and go out, well, they will always form a plane. They will always be on the same plane. It might not be the x, it might not be the horizontal, that xy plane. It might not be yz plane, but it's going to be some plane. So as far as the angle between them, the formula is exactly the same. You're talking about the angle between two vectors. So all you do is dot the two together, divided by the product of their magnitudes, and then inverse cosine to find the angle. And for the same reason, since cosine of 90 is equal to 0, if these u dot v is 0, that means the vectors are orthogonal to each other. They're at a 90-degree angle. Remember that? So if I want to find the angle between these two vectors, well, I need to do all those parts. So cosine of theta is going to be equal to, what do I get when I do u dot v? 14. You get 0 plus negative 1 plus 15. What about the magnitude of u? Or v, doesn't really matter which one. Square root of what? 26. 0 plus 1 plus 25. What about the other one? Yeah, 16 plus 9 is 25, plus another 1 is 26 again. So my denominator is, so that simplifies to 7/13. So my answer is 7/13. No, what else do I have to do? Inverse cosine. So theta is going to be equal to the inverse cosine of 7/13. Go and punch that in.
1.002.
My guess is that's radians.
Oh yeah. Good guess.
What do you end up with?
57.
Anybody else? 57.4? Okay. Not too bad. Okay. Now, parallel vectors. Parallel ends up kind of strange when you're talking about vectors because you can reposition them wherever you want. Location does not matter. All it is magnitude and direction. So as long as the direction is the same, they are considered parallel. The length doesn't matter either. So the easiest way to figure it out is to move them again to the origin as their initial point. So turn them into component form. And as long as it's a non-zero vector, if you multiply one vector and can get the other one, they're considered parallel. Okay? So as long as I can show this statement to be true, they're parallel. So all three of these lines would be considered parallel to each other. Because they all are going the same direction, they're just not at the same location. And even going the opposite direction is just multiplying by a negative. So, which of these vectors would be parallel to the vector w that starts at 3, 0, negative 1, ends at 2, 1, 4? Well, what would I have to do first? Do what? Component form for w. So vector w is going to be equal to what? Negative 1, 1, 5. 2 minus 3, 1 minus 0, and 4 minus negative 1. So, which one is that the same as? Or parallel to, I should say. How do you know it's parallel to B?
Because if you multiply by -6,
Yeah, if you take negative 6 times vector W, that equals vector V, right? So because of that, V is parallel to W. Now something a little bit different. Determine whether these 3 points are collinear with each other. Do they lie on the same line? Now remember, from a vector standpoint, location doesn't matter, right? So if these are on the same line, that means any line formed by these are what?
parallel.
Parallel to each other. So the only trick is to actually generate some vectors. Instead of just those points, if I turn this into PQ and QR, are those parallel to each other? Well, what's P to Q in component form? What'd you say, John?
Which do you choose as like the terminal?
Does not matter, because if you switch it to Q, if you switch it from Q to P, this would just be 1, -5, and 5, right? So the multiplier would just flip signs. So yeah, as long as you're picking 2 different points, you're fine. What's the other one? 6, 9, and -3. Where you get that? Yeah, I was just checking. Are they collinear? Why not? Yeah, they're not parallel to each other. So since the vector PQ is not parallel, I should actually write it out in words, but let's go like that. Sure, that's a symbol. Is not parallel to QR, then, or therefore, if you want to get fancy, P, Q, and R are not collinear.
Now, if those two worked, would you have to check it with RP as well? Or no?
Should you? I'm trying to think of a circumstance. I don't think you'd have to, because the thing is, you're basically, by repositioning them, if they're on the same line here, so say it's going from the center out this way, right? By moving that other one down to the same place, even if it's going this way, well, the only way that's going to happen is if I did P to Q, so that's coming from here to here. Do you see how they all would have to end up being on that same line
Alright.
by moving them? So no, you wouldn't have to test the other. As long as you can show it with 2, it's going to be work for 3. At least I can't think of a circumstance where it wouldn't. Okay, one more. The initial point of the vector v, 6 with -1, 4, is at 0, 2, -3. What's the terminal point? So this is thinking about it a little bit backwards. Any ideas?
It was just add it to
Add what?
add v to 0 to
Why?
because that's I don't know. Never mind.
I didn't say you were wrong.
You should add v to p.
Why?
Because v is like how far on each axis the vector goes.
Yeah, that's the difference between them, right? Vector v is just equal to the coordinate q minus p, right? So if I have vector v is 6, -1, 4, that's equal to, well, I don't know what q is, but let's say x minus the, where's p at? 0, y minus 2, and z minus -3. In order for that vector to be true, this would have, x, y, and z would have to be your q coordinate, right? So, what do you get?
6, 1.
6, 1, and... Yep, 6, 1, and 1. Oops, and that should not be, because it is just a point in 3 space, not a vector. Questions on any of it? Okay. Tomorrow we will do one quick problem right at the beginning, but I want to give you guys time to work on some of the other ones before we jump into the harder stuff. Get to work.